All right, everybody. Good morning.
Good morning.
So there's a couple things I want to talk about before we get into stuff today. We got some things we got to fix. And if we don't get it fixed, you're only going to have a lot of trouble in biochem. So I graded the exam. And I expected better, I'll be honest with you. And so what I'm going to do, because we got to fix this. That's the important thing. You got to know this stuff before you get to biochem. That's my goal for you, okay? I don't really care about the A, B, C, D, F. I care about what you learn and what you leave with, okay? So what I'm going to do is I'm going to start scheduling an extra office hour every week from now on. And this weekend, if you can, I'm going to schedule 2 workshops on Saturday and Sunday. You can come to either one. If you come to them and you work through the problems, I'll give you half your missed points back. Okay, so another opportunity to get some of your missed points back. So I'll send out some emails, we'll take some polls. You don't have to attend both of them, just find one that fits your schedule. You'll come in, you'll rework your exam with me present, and we'll go through. I need to find out where the problem is in terms of the mechanism. I can't stop in class because we've got to get through this material before you get to biochem, okay? And so that's what I'm interested in. Is everybody okay with that?
Yes, sir.
All right. Will everybody give me their efforts?
Yes, sir.
All right. You do.
Okay, what if that doesn't work for us? And can we?
What does it mean by that doesn't work for us?
Like, I'm going home this weekend
Okay.
for a family event.
Okay.
So, can I just do test corrections at home?
No, we got to do a workshop kind of thing.
Oh my god.
Hold on. Don't panic. Don't panic. Don't panic. I can schedule another one. I can schedule.
I'm during the test because my printer wouldn't work, and I tried it the night before and all this stuff, so I didn't have half my notes in the first place. And then I was afraid to ask if I could use my iPad.
No, it's got to be printed. It's got to be handwritten
Exactly,
stuff. Yeah.
So
Nothing with
I'm
internet
screwed.
access. So how about we do this? I'll do 3. Can I schedule one for an evening like next week?
Yes, I could do that.
You can do that? That'll work? All right.
What times were you thinking Saturday and Sunday? Because I work 6 to 3 both days.
6 to 3, 6 being a.m.
6 a.m. to
Uh,
3 p.m.
I can. Why don't I send out an email? Let's find out what the time. But I was thinking in the afternoon. So I know some of you got church things on Sunday, and I respect that. So I'm not going to try to interfere with that kind of stuff.
How about like Thursday evening? Like, since we don't all have it off because we're 1 a.m.
The problem with Thursday evening, is I can't guarantee you can get on campus easily.
Yeah, no.
With the part, it's going to be a mess
Is it?
with the football game.
Oh yeah. It's gonna be chaos unfolded.
Okay.
It's gonna be twice as much as before.
Okay.
10 times as much.
All right, we good with that? Well, we've at least got a plan moving forward.
Yes.
All right. So what I want you to do is I want you to relax about it. We're going to learn through this. Pardon? Silly.
Did you post the grade?
I have not yet. I graded them this morning.
And also, are we like not doing the rest of chapter 8?
We are. What we're going to do for chapter 8, finishing up, is going to be on the board. Okay. So I don't have really good slides that cover the stuff for this book in terms of chapter 8. And so on the ethers, everything that I have already built out is actually pretty in depth with ethers, and this class just doesn't go that far in depth
Okay.
with ether chemistry.
So we still have to like do it in the book, right?
Oh yeah. But we're going to cover it on the board. We're going to cover the last part of ethers, right? And so, so I'm going to ask you, what is an ether?
Two alkyl groups attached to an oxygen.
Okay, so we've got 2 alkyl groups of some type attached to an oxygen. And R and R prime can either be the same or they can be different. And you all have already learned how to make ethers through the SN2 reaction. And in fact, it was on the exam, right, where I took some alkyl halide and you reacted that with an alkoxide, right? And I believe on the exam, DMSO was the solvent. So you knew you had a good nucleophile, you knew you had good leaving groups, you knew you had a polar aprotic solvent. This has to be an SN2 reaction. So the nucleophile attacks, the leaving group leaves, and you make an ether, right? Huh?
Dimethyl.
In this case, dimethyl ether, yeah. We're not going to focus too much on the nomenclature of ethers. But we could have had a different alkoxide that had different stuff here and different alkyl halide. We could have made it to where these sides weren't the same. So this is one way in which you can make ethers. It's called the Williamson ether synthesis. Okay, it's a named reaction. You will quite frequently hear organic chemists say, I'm going to do a Williamson ether synthesis, blah, 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 blah. We use a lot of named reactions, okay? Ethers, by and large, are fairly unreactive. Okay, so when you all go into the lab and you do some of the chemistry that you're doing, quite frequently you'll use ether as the solvent. Okay? Usually what you use is diethyl ether, which when you put the lone pairs of electrons in, looks like a bat, right? So you have a bat flying around. How might we make diethyl ether using the Williamson ether synthesis? What would we need?
Ethyl iodide.
Okay, so if I took ethyl iodide, and what would I need to react that with?
Ethyl side.
Yeah. So I can take those two things, react them together, and in an SN2 reaction, make diethyl ether. Okay? There are other ways to make these ethers, but really all I want you to know is the Williamson ether synthesis. Okay? So the general preparation of ethers is through the Williamson ether synthesis. It is typically an SN2 reaction. There are examples that are SN1, but we're going to keep it simple. We're going to keep it just to the simple ethers. Okay? Ethers have one thing kind of in common, and that is they're all pretty flammable. Okay? They burn. That's about all you can do with them. You can burn them. Okay? And so, again, that's why they make good solvents. They don't react with a whole lot of stuff normally. So that's pretty much all there is for the simple ethers. But there's another class of ethers that we actually changed the name for, and we call them epoxides. And they're three-membered rings. 1, 2, 3. Okay, they form a three-membered ring. Those are called epoxides.
Could you spell that?
Epoxide, sure. You all are familiar with epoxides, believe it or not. Epoxy glues, right? If you've ever used epoxy, this is the functional group that is involved. This ether is more reactive than that ether. Can you tell me why?
There's only two bonds, there's only two carbons, no, back up the truck, semi-truck.
Okay. Why?
1, 2, 3, 4.
Oxygen bound to an R group, oxygen bound to an R group, oxygen bound to an R group, oxygen bound to an R group. What's different?
Structure.
The structure is certainly different, but what about the structure makes them more reactive?
The dipole.
They do have a dipole, maybe a little bit more than a regular ether, but that's not it. It is because it's closed. That's going down the right path. But what about being closed? What kind of hybridization do you think those carbons have?
Is it because it's like unsaturated?
It is unsaturated a bit, yeah, but that has as many hydrogens as you might think, but neither does this one. Is it sp2?
I mean SP.
How many, do we have any,
One?
do we have any double bonds?
No.
So it's sp3. Right, and sp3 carbons look like this, don't they? They look like a tetrahedron. And when we put them together, right, they're nice and they can have conformations, right? Can we rotate around that very much? If we put in no, it's going to lock it, right? But that's not the reason. So let's see what happens. Now this is an oxygen atom. I'm going to put an oxygen atom on here. Now I've got to connect these things together. Look what starts to happen to my model kit. What can you tell me about the bonds? They're very strained. They're bent. They're not happy. Listen to it when I pull it apart. Listen to it when I pull it apart like that. Where does that extra pop come from?
Angle string.
Angle strain. It is a strained bond. It's an sp3 hybridized carbon, technically. Okay, we're not going to get into the technicalities here. But notice how those bonds are all strained. So it would much rather release that strain. Okay? And so epoxides are actually very reactive compared to other ethers. They're a special brand of ether. Okay? Now, you can't really make them through the Williamson ether synthesis that we just learned, but you can make them from a reaction of an alkene. So let's just pick on an alkene, the generic alkene here. We don't really care what's attached to it. I'm just going to put some methyl groups, okay? And we're going to react that with what's called a per acid. So don't worry about what R is. It doesn't really matter. And I'm going to put in some color here. So instead of a regular carboxylic acid, right? So a regular carboxylic acid, right, looks like this. There's an extra oxygen that I've colored red. Okay? Which oxygen atom do you suppose ends up in the epoxide? It's the red one. That's right. I colored it for a reason. And so when you react these two things together, what you get is this. Plus so these so-called peroxy acids or per acids can deliver an oxygen atom to an alkene to make an epoxide. This is called epoxidation. The named reaction is epoxidation. This is an epoxidation reaction. I don't want you to know the mechanism for this. There's a lot of arrows that flow around. Okay? But what you need to know is that whatever the configuration is of the alkene, that configuration remains in the epoxide. That must mean that the two bonds to carbon and oxygen happen at the same time. Okay? So if Jason came in and used this alkene, what's the configuration?
SP2.
No, it's sp2, but what's the configuration of the two groups?
Trans.
They're trans. The two methyl groups are trans. So if he reacts that with the per acid, he will get the trans epoxide, where the two methyl groups are on opposite sides of each other. If he started with the cis, he would get cis. Okay? That's the thing that you need to know in terms of making epoxides. Okay? It's not the only way to make epoxides, but it's the easiest way to make epoxides. Okay? I did a lot of work in my postdoctoral studies with peroxy acids for a while. Yeah?
Could you do an example of a cis reaction?
Yeah, sure. Why not? Let's look at one. Let's do a real easy one. So you all tell me what so let's say you took this alkene and you reacted it with a per acid. That's a 3 there. What's the product?
The oxygen is gonna coming out that side.
Yeah. That would be the product. We would have what we called a 6-3 fused ring. So we got two rings, right? We got the ring that has the 6 carbons, then we have the 3-membered ring, and they're stuck together, right? Now that's cis, right? This group and this group are on the same side. It just happens to be part of a ring. I could also just as easily do something like this, right? Since there's ring strain in this, what do you think would happen if I threw in a nucleophile? So let's say I took this product from this reaction, and let's say I throw in cyanide, which is a nucleophile. Let's just say I throw in some sodium cyanide and I use DMSO as my solvent, so everything solubilizes. What's going to happen?
Would it be an SN2 reaction?
Sort of.
So would like the our nucleophile attack?
What will it attack? What do nucleophiles attack?
Bases.
Well, they are bases.
I would like the yeah.
What do they attack? Do they attack protons? Do they attack carbon?
Carbon.
They typically attack carbon, right? So which carbon would it go after?
Would oxygen leave?
Okay, that's a good idea. How would you do that?
So would oxygen leave first, or kind of?
Okay, if it left first, I'd get a carbocation, right?
That's true. Okay, then would it like like the bonds would be forming and breaking at the same time? And then
Okay.
the oxygen leave, and then the cyanide attacks where the oxygen was.
Okay, so I could have the cyanide, right? Attack one of these carbons, and it doesn't matter which one in this case because they're identical, right? And then what happens is those electrons go to oxygen, right? So we're going to break this bond and we're going to form this bond, right? And so my product would be that would be my product. So nucleophiles typically like to attack epoxides and open them up. That does not happen with a regular ether. If I took sodium cyanide, DMSO, and I put dimethyl ether in there, nothing would happen. Because alkoxides, or O- are typically very, very bad leaving groups. Why is it a good leaving group here? That ring strain, right? Because when the nucleophile attacks, right, it will relieve that ring strain. And that's very important. So if that's our epoxide, right, the nucleophile comes in and attacks, and when it forms the bond here, it breaks and forms that. So this actually can be a pretty good leaving group. Why did I say this really wasn't an SN2 reaction? Because the leaving group doesn't actually leave from the molecule, right? But otherwise, it looks exactly like an SN2 reaction, right? It's just that this oxygen just didn't go floating off out into space like it does if it was an alkyl halide, right? So that's what nucleophiles can do to ethers, is they can ring open the ether, okay? Now in your book, they oversimplified it and said that you're always going to attack the least substituted carbon. Now you can't tell in this one, right? But if you, let's look at an example that might be more relevant. So let's say we took an epoxide that looks something like this. So it's got a methyl group here. And the nucleophile will attack the least substituted carbon. Why do you think that that should be the case?
It's more space around the carbon.
Yeah, there's nothing for it to bump into, right? The nucleophile can get here really, really easily and break open that and give me the product. Okay? This is true anytime you have a negatively charged nucleophile. Okay? If you have negatively charged nucleophiles, this is true. It will attack the least substituted carbon of the epoxide. Okay? It's not the whole story, but since your book doesn't go into the whole story, I'm not going to go into the whole story either. If you're under acidic conditions, it actually does the opposite. Okay? But we don't need to go into why. Okay, so that's the mechanism for any nucleophile attacking an epoxide. So, what do we need to know? We need to know what nucleophiles will do this, right? So let's do this. Let's make a table. Let's just say we're not going to do that. Let's make it real simple. So if we take a nucleophile plus an epoxide, and we're just going to use a generic epoxide, we know we're going to ring open that and get this. Okay? All right.
Well, how come it's strands over there?
Well, it doesn't matter. It's single bonded, right? So it can rotate. It's got free rotation. And then, of course, you can imagine working the reaction up with a little bit of acid and water, which is usually what you do at the end of an organic reaction. And you would get an alcohol. Okay? So really, I can open up epoxides and get some type of alcohol as the final product, which is kind of nice. Another way to make alcohols, right? So what kind of nucleophiles could we have? Give me some examples. What nucleophiles have we learned about so far? OH minus, right? And if we do that, we would get that molecule, right? What if it was cyanide? We would get that molecule. What other kinds of nucleophiles could we have?
We have like halides.
Okay. Let's say X minus.
Yeah.
In theory, we could do that. Yep. In fact, that's called the halohydrin. Remember we learned about halohydrins before? It's another way to make a halohydrin. What else could we use?
Something with sulfur.
Salt, yeah. So we could use something with sulfur that's negatively charged, and we can get that kind of molecule. We can even use other carbon type nucleophiles, so we could use the C triple bond C nucleophile, right? And we can make new carbon-carbon bonds. Get that kind of molecule,
Yeah.
right?
Yeah.
So all of the nucleophiles that we've talked about so far in the SN2 reaction technically can react with an epoxide and give a whole slew of different kinds of molecules. Okay? That's the take-home message here. Ring strain. Why is there ring strain?
Why is there ring strain?
Yeah, tell me why. That's a very important concept. I built a model. We saw that it was strained, but why does the ring strain exist?
Because
Because it's connecting them without a fourth bond. Like they're far away.
That's right, because where the orbitals are pointing, they don't really want to overlap very well, all right? And if we started to add more and more carbons, that ring strain would go away, right?
Yeah.
But it's really tiny thing. And remember from math, right, when you took trig, what do we know about 3 points?
120 degrees.
Not that part.
Oh.
You're not wrong. But what about 3 points? They always define what? A plane. These three atoms must be in the same plane, right?
I know.
Yeah. And so you're taking something that wants to be tetrahedrally shaped, right? Because it's sp3. And remember, tetrahedron kind of looks like a pyramid.
So why does a ring strain exist?
Pardon?
Why did you say a ring strain exists?
Because you've got 3 bonds that can't overlap very well. See the little buckles that were starting to form? It's because things don't want to, because these are supposed to be at 109.5 degrees, right? If you look at a tetrahedron, that's the bond angle. But now, as was pointed out, that angle is way away from 109.5. And so it's just got a lot of strain built up in it. And you can really see it in the model. I mean, I would highly recommend you all not do this to your model kit. Okay? But you can even hear the strain being released. You know, when I just take two carbons and pull them apart, I don't hear that strain, right? But I certainly do when I try to pull apart from a third party. All right. So that finishes up ethers. Ethers and epoxides.
And was that like all of the rest of chapter 8?
Yeah, that was pretty much so the rest of chapter 8. So the take-home message is, how do you make epoxides?
Take away carbon.
You take an alkene plus
Peroxy acid.
peroxy acid, right? And you can use any peroxy acid. That's why I just used R. Okay? So if you see C double bond O, OH, right? So whatever, over here, OOH, that is a peroxy acid. We frequently abbreviate that as RCO3H. Those are equivalent. Okay? Those are equivalent ways of writing the same thing.
Is there a name for that reaction, sir?
It's just called, we just call it epoxidation. It doesn't bear, to my knowledge, it doesn't bear an individual's name.
Yeah.
I'm sure somebody somewhere discovered it, and I am sure that somebody somewhere knows that it's named after so-and-so, but it's not popularly named. Okay?
So how do we know that it's a peroxy acid? Is it just gonna have that format, CO3H?
Yep. Yep. You're going to have,
So basically, if it looks like the structure, if it has the functional group of a carboxylic acid or
with an extra oxygen.
ketone with an extra oxygen.
Yeah, so you're going to have this. You're going to have that, and that for a peroxy acid. That's the functional groups.
Okay.
Or the functional group is all those things put together, I should say.
So it has to be the 3 of them.
Yep, you got to have 3 oxygens. All right. So today we're going to talk about probably my second favorite topic, is aromatic compounds. When you all hear the word aromatic, what do you all think? Smell. Think of anything else? Perfume? Cologne? This is not what chemists mean by aromaticity. Okay? It is true that back in the day, things that typically had a pleasant odor were what chemists would call aromatic. But that's not what we really mean anymore. A lot of what the things that make your perfume smell better, smell good, have nothing to do with chemical aromaticity. Okay? We're going to talk about, today we're going to talk about benzene, and we're going to talk about the stability of benzene. We're going to talk about molecules that contain benzene. And I just kind of want to get a gauge of what do you all already know about benzene. Have you ever heard that word before? Benzene.
Yeah.
Yeah, what do you know about it?
It's a 6-carbon ring.
It's a 6-carbon ring. Okay, so we're going to be dealing with a ring again. It's got 3 double bonds.
Kind of, but they're delocalized, so
They alternate?
They do alternate. That's right, they alternate. Have you all heard anything in the popular media about benzene, perhaps?
I have a question. Is that not gas? Like, is benzene not like petrol that you put in your car?
Yeah, so there is benzene and benzene-like molecules in automotive gasoline.
I don't know if this has anything to do with it, but benzene and the word benzene in Arabic means gas.
Means gas?
Like the fuel you put in your car.
Okay. Interesting. Yeah. So, when it was discovered in the soot that was obtained from gas lamps. So if you've ever had a gas lamp in your home and you know the glass ball that goes over it, it'll get soot. You can take that soot and you can actually get benzene out of it. It forms benzene in the burning process. So maybe there's some relation there, perhaps, in terms of why that name is similar. Have you all seen on TV the ads for these attorney companies, contact so-and-so for Camp Lejeune? What have you heard about at Camp Lejeune?
There's like something with the water
contaminated groundwater that led to cancers and other types of deals. What happened at Camp Lejeune was they used a lot of benzene. Actually, we use a lot of benzene industrially, but it has a habit of seeping into the groundwater, and it's also carcinogenic. Okay, so benzene, I used to be able to go over to the stockroom and buy a gallon of benzene for like $5. It was cheap. It's cheap stuff. But now it's like $100 because they're trying to limit people using it because of the carcinogenic properties it has. So you want to stay away from benzene and benzene-like molecules. Okay, they can be carcinogenic. When I grew up at home, we had a BF Goodrich tire plant. It was the largest tire manufacturing plant in the world at the time, in my little tiny hometown. And the rubber workers worked with benzene. They had 5-gallon buckets of benzene next to them, and they would take their hands and they would dip a rag in it or whatever, and they would use that to help peel back the rubber adhesive when they would make a mistake. My grandfather worked there. My grandfather died from brain cancer, in part because, I believe, I don't have any real evidence for this, but he spent 30, 40 years of his life around big open vats of benzene every day. And so the groundwater in my hometown where I grew up, they are monitoring it because there was this huge tank of benzene that they discovered had been leaking for like 15 years into the groundwater. And so remediating this kind of stuff is not easy. So you all have probably heard about benzene, okay? But benzene is special in chemistry. Now, I didn't have all this stuff ready for the demonstration. We'll do that on Wednesday. But as Jason mentioned and others, we have a 6-membered ring with 3 alternating carbon-carbon double bonds. Okay, now you'll notice I've made all of those bonds about the same length. Okay? All 6 of these carbons are put together. Now the way that you build a benzene ring in your model kit is you take 2 of these sp2 grade pieces and you take one of these double bond pieces and you snap them together like this. And you take 3 of them and you put them together like this. If I can get the right connecting piece. I've just built a model of benzene.
That looks pretty neat.
And what do you notice about all 6 carbons?
Planar.
They're all on a plane, aren't they? They're all in a plane. And you'll notice if I try to bend it, it doesn't want to bend very well, right? It's nice, planar. All of the carbon-carbon bonds are exactly the same length. When I'm kind of roughly measure it, you can see that they're all about the same length, right? But that's not what we would expect if this really was 3 carbon-carbon double bonds. If these really and truly were 3 carbon-carbon double bonds, we all learned, right, early on that a carbon-carbon double bond is shorter than a carbon-carbon single bond. So you would expect benzene to look something like this. A long bond, a short bond, a long bond, a short bond, a long bond, a short bond. But that's not how benzene is. Benzene has identical carbon-carbon bonds whether they are the single bond or the double bond. They're exactly the same length, okay? All of equal length. How do I know that? Other than just looking at the model. How do I know that?
Magic microscope?
Magic microscope, that's right. Turns out that you can freeze benzene and it will grow a crystal. And you can put this crystal on what's called an X-ray diffractometer and you can get a picture of it, basically. And when you look at that picture, you'll notice that all of the carbon-carbon bonds are identical in length, okay? And this really puzzled people for a long time. This really puzzled people for a long time, okay? So let's just do an example. So let's say I have benzene, and let's use another color down here. And let's say I have cyclohexene. This is the demonstration we're going to do on Wednesday, okay? I couldn't find my cyclohexene this morning. How are those 2 molecules similar and how are they different?
They're both rings.
Both rings? Okay, 6 carbons in the ring. They both have at least some pi bonds, right? But this one has 3 pi bonds, this one has 1 pi bond, right? And you all know what this can do, right? This can do, it's just an alkene, right? So what can we do with it?
Addition?
We can do addition reactions, right? So you all learned, for example, that we can take bromine, and when we add bromine to it, what happens? What happens when you have an alkene and...
2 BRs from the double bond breaks and.
That's right. So you're going to end up forming,
Trans?
and it's going to be trans. I'm not drawing in the stereochemistry here, but that's what you get. Yeah. You get bromine addition across the carbon-carbon double bond. Does anybody know what color bromine is?
Blue.
It's not blue. It's kind of an orangish brown, reddish, kind of yucky looking color. Yeah. Alkyl halides, what color are they? They could be a little yellow, but really they're kind of colorless for the most part. So something that's colored reacts with something that's colorless to give something that's colorless. Okay?
You say colored, the bromine is colored, the
Yeah.
alkene is colorless, and it gives a colorless,
Gives a colorless product, yeah.
that's,
So if I took bromine, and this is going to be the demonstration, if I drip it into this, you'll see that the color goes away.
that's cool.
That is cool. But if I
How does the
take,
color go away?
huh?
How does the color go away?
Let's talk afterwards. I can tell you how it does. Now, if I take benzene and I add bromine, if this benzene was really 3 alkenes stuck together, we would expect that it would do an addition reaction, right?
Yeah.
We would expect that it would add just 3 equivalents of benzene or of bromine and make something that looks kind of like this. This is what we would probably expect, right? That's what we would expect. This doesn't work. In fact, when I add bromine to benzene, the color of bromine remains. Benzene does not do addition reactions at all for all practical purposes. If I take cyclohexene and I put hydrogen gas in there and let's just say palladium, what happens?
The hydrogens add and resist.
That's right.
It just becomes regular cyclohexane.
That's right. It just becomes that, doesn't it?
Yeah.
That's what it becomes. If I take benzene and I put hydrogen in there and palladium, nothing happens. No reduction. In order to get benzene to reduce, add hydrogen to make cyclohexane, you've got to use 1,500 pounds of pressure of hydrogen gas, and you got to heat it up really hot for it to happen. It won't happen at room temperature like this one does. So what does that tell us about the carbon-carbon double bonds here?
Is it like super duper stable because it has like double bonds for some reason?
Yes, it is. It is super duper stable. And that super duper stability, because I can't say that word very well, right? Chemists don't go around and say super duper stability. We say aromaticity. That's what aromaticity means. It's unexpected stability, right? So these carbon-carbon double bonds, because they are located the way that they are, because they're alternating, they add to the stability of the molecule. Yeah.
So what does the reaction of a benzene with the bromine look like?
It doesn't do anything.
It doesn't?
Doesn't do anything. It just sits there and stares at you. It's just bromine and benzene. Doesn't do a thing. Okay? Now, point 1, it says it contains a 6-membered ring and 3 additional degrees of unsaturation. What does that mean? What is the formula for benzene?
C6H12.
Oh, H6.
Oh, yeah.
It's got 4 degrees of unsaturation. Remember, a ring
Yes.
is an unsaturation, and each double bond is an unsaturation. So there are 4 degrees of unsaturation here. How many are for here? 2. 2. The ring and the pi bond, right? Okay. Now, if you look at the bond lengths, again, looking at our magic microscope, if I could look at ethane, CH3CH3, right, that's about as simple a single bond as you can get. What you would notice is that the bond length is about 1.5 angstroms. So let's just say it's the length of this pin, okay? If I looked at ethylene, taking 2 hydrogens away and adding 1 unit of unsaturation, making a double bond, what can I say about the bond length? It is shrunk by just almost 0.2 angstroms, right? So it's like that long.
Okay, so if we have 3 pi bonds, and that's what makes it like that, what if you had 2 pi bonds?
Wow.
That would that, I guess it's not benzene, but like.
It's not benzene anymore.
What is it, but is it like somewhere in between, like is it more stable than 1, but less stable than 3?
It is. Well, the answer truly is it depends where those double bonds are. But if those double bonds are double, single, double, skipping, then yes, it is a little more stable.
So the alternating gives it more stability?
It does. We'll get to that. We'll get to that in just a minute. Notice where benzene's bond lengths are. Almost right in the middle of those 2. So it means that the single bonds really aren't fully single bonds, and the double bonds really aren't fully double bonds, right? It's something special, and it has to do, and Selena was getting close to it, it has to do with the fact that they are alternating, okay? What do those red arrows in the middle of that benzene ring mean?
Resonance?
Resonance. What is resonance? We talked a little bit about it, right?
Change of location to double bonds of the pi bond.
Yeah, but can I just always do that?
Oh, if it's connected to 2 of the same things.
So what does this arrow mean when I do this?
Oh, doesn't it mean like the pi bonds could be on those 3 or those 3?
That's right. So I can move this pi bond between these 2 carbons, right? I can also move this pi bond here, and I can move that pi bond there. And what I get is a resonance structure.
And don't resonance structures, like we draw them that they're both because we don't really know which one they're on?
That's right. That's exactly right. These electrons actually aren't in that pi bond, nor are they really in that pi bond.
Somewhere in the middle.
They're all the way around the molecule, right? Each and every one of the carbon atoms of benzene is sp2 hybridized, and each one of these carbon atoms has a little electron in it. Okay? You will quite frequently see people write this as
The circle in the middle.
with a circle in the middle, where it's showing that all 6 electrons are actually completely delocalized across those 6 carbons. And so you can draw lots of resonance structures from benzene, and the more resonance structures that you draw, the more stable the molecule. And in this particular case, it's really stable. Okay?
Wait, the circle means that the electrons are circling all around?
Yep. That's really what it means. Those electrons are completely going around in a circle, if you will. That's kind of a lie, but it's pretty close to accurate, right? There's an electrical current that is created within benzene that we don't need to talk about. Okay. And so, you know, this is actually pretty remarkable if you think about it. Benzene is so stable, it will be around for hundreds and hundreds and hundreds of years without anything happening to it. That's why it's so problematic in groundwater. It don't go away, right? Now, naming benzene, pretty straightforward kind of stuff, but there are a few things that you need to know. So when you have one group attached to a benzene, we typically just name the alkyl group as an alkyl group and then just add the word benzene. So notice I've got an ethyl group attached to benzene, that becomes ethyl benzene. I've got a tert-butyl group attached to benzene, we call that tert-butyl benzene. I've got a chlorine group or chloro group attached to benzene, we call that chlorobenzene. Okay? We also have some common names that you need to know. If I put a methyl group attached to benzene, you might say, well, that should be named methylbenzene. That would not be an incorrect name, but nobody calls it that. Back before we had this more systematic name, people called methylbenzene toluene. And notice it's got a benzene ring with a methyl group attached to it. Okay? Now here's something that's going to kind of blow your mind a little bit. I just told you that benzene by itself was carcinogenic, right? So ladies, if you went and bought nail polish remover, it would not contain benzene, but it does contain toluene. Okay? Putting a single methyl group on benzene makes it go from carcinogenic to relatively safe. It's just putting a CH3 on there makes a big difference in how your body reacts to it. Okay? So that's toluene. If I put an alcohol, so this would be hydroxy, right? It's a hydroxyl group, so hydroxybenzene. That's called phenol. If you've ever used Chloraseptic when you've had a sore throat, they put phenol in Chloraseptic. That's what helps deaden the scratchy feeling in your throat. And then putting an amino group, an NH2 on benzene, you might say, well, that's aminobenzene, and that would be correct. But we call that aniline. Okay? Aniline is one of the biggest industrial chemicals kind of made in the world. You use anilines to make things like dyes. You also use aniline to make things like explosives. So it's a
What
dual.
about toluene, like TNTs, like?
Oh, yeah, TNT, trinitrotoluene. So putting some NO2 groups on, but we're not going to talk about that today. But interestingly enough, since you bring it up, Jason, there is soil around the United States that is still considered explosive from World War II. Back in World War II, obviously we needed a lot of explosives, right? And we were making it quickly, and they would take toluene and they would nitrate it to make TNT. And then when they were done, they would just throw the stuff out and back because we were in such a hurry. And there is literally, in places, there are pieces of property that are so contaminated with TNT that it's considered explosive. And they're trying to remediate that now. So better living through chemistry in that regard, I guess.
Wait, what do you, so, what would, like, does that mean it's like, what do you mean explosive? Like, if I just step in it, it's just gonna explode, or does it need like some sort of
You
fire,
could
or-
step in it, but it could be detonated. I mean, you can literally take the soil and you could put a blasting cap in it and you could make it a small amount of it if it was packed right, explode. Kind of interesting. You can also name things that have more than one substituent, right? So you can imagine having two substituents on benzene. If you look at this, right? I've got a bromine on carbon number 1, I've got a bromine on carbon number 2. It's a 1,2 disubstituted benzene. But we don't say 1,2 disubstituted. We call that ortho. These bromines are ortho to one another. This is known as ortho dibromobenzene. Okay? And they usually just abbreviate that with an O. You can also call it 1,2 dibromobenzene. I would accept that. That's still a reasonable name. If I have my two groups in a 1,3 pattern, 1, 2, 3, so 1, 3. This is called meta. This is meta dibromobenzene. And I can have them in a 1,4 relationship, and we say that that is para. So that is 1,4 dibromobenzene or para dibromobenzene. So if you saw that, how would you name that right now? 1,4.
I want to say dimethylbenzene, but again, it's like the common name is toluene. So
It's not though.
it's still dimethylbenzene.
It's still dimethylbenzene.
Okay.
Actually, this one has a common name too that we're not going to get into, but that would be 1,4-dimethylbenzene or para. Okay. So you can name these.
Oh, so the para or the P goes instead of the numbers?
It does.
I thought, okay.
Yep. So P means 1,4, meta means 1,3, and O means 1,2. Yeah. Ortho, meta, or para? Meta. Yeah, it's 1,3, right? 1,3.
So I was just counting carbon.
Okay, yep. Same number of carbons.
Yeah, I was just doing the order number, like.
Okay,
one,
yeah.
two,
1, 2, 3, 4. 1, 2, 3. Are these the same molecule?
No.
No.
They're not. They have different structures, don't they? They have different boiling points. Here's a molecule that is aromatic. It's not benzene by itself, but it is an aromatic molecule. If you look at it, can you see the benzene rings in it? You can kind of see a series of benzene rings. This is called benzoapyrene. This is what happens when you smoke cigarettes. This gets formed from the burning of tobacco. It is highly carcinogenic. Not itself. Your body actually metabolizes it into something that's carcinogenic. Okay? Just like our body metabolizes benzene into something that's carcinogenic. Okay? But that is an aromatic molecule. Here's some other aromatic molecules that might be of more interest to some of us. So this first one, okay, how many benzene rings do you see? I see 2. I see a benzene ring here, and I see a benzene ring there, right? This is Zoloft. Okay? This is, well, it's a drug that's used for a number of things, depression being one of them. So that molecule right there contains benzene rings. The molecule here in the middle, this is Valium. How many benzene rings do you see there? 2, yeah. Novocaine. How do you all know Novocaine?
It's like a pain thing when you get teeth stuff.
That's right. When you go in, before they give you the drill, right? They deaden your mouth and you come out and you talk on funny and all that kind of stuff, right? That's Procaine. How many benzene rings do you see there?
1.
I see 1 benzene ring. And notice, it looks like it's not just a regular benzene ring, right? It looks like it's an aniline. Right? We got the aminobenzene piece there, right? We used to have students, when I was a graduate student, actually make Novocaine as one of their labs. And it was kind of cool, except people started losing the feeling in their fingers and because they wouldn't be, so we stopped doing that. Viracept, right? How many benzene rings do you see in Viracept?
1, 2.
I see 2. One of them actually has an OH on it. You would think that that's a phenol, right? Right? So this is a drug used to treat HIV. Viagra, the little blue pill, right? There it is, sildenafil. How many benzene rings do you see there?
1.
I only see 1 benzene ring, yeah. Something that starts to look like a benzene ring, but not quite, right?
Yeah.
And then Claritin.
Isn't that a painkiller or like a cough? I don't know.
All right, Claritin, what do we use Claritin for?
It's an allergy medication.
Yeah, and you get to get it over the counter, right? Right. So if you have seasonal allergies, it's an antihistamine, right? And you see something right here, right? That's benzene. But here we've got something that starts to look like benzene, but has a nitrogen in the middle. Okay, it's pyridine. We won't talk more about pyridine today, but it too is an aromatic ring. It has six atoms and alternating double bonds.
So when you say aromatic ring, are we talking about stability? We're talking about stability, right?
Right now, we're talking about a 6-membered ring that's stable. Yeah.
Okay, and that's what aromatic means.
Yep. For right now.
For right
for right now. We're going to expand our definition of aromaticity here in just a bit. Yeah. But what I want you to take away from this is there's a lot of things out there that many people depend on that depend on benzene. And so benzene by itself, carcinogenic, bad for the environment, yada, yada, yada. But I take benzene and I do other stuff to it and I put other things around it. And now I have very interesting molecules that can, help me endure my dental procedure or help curb my depression, right? So there's a lot of different things that rely on benzene rings. All right, so now I said we were going to expand our definition of aromaticity. We're going to start that right now. So there are a few things, pardon?
6.
6.
Yeah, 2, the N and 4.
Yep, we're going to start talking about that, yep.
I was reading.
That's okay. So there are a few things that have to be present for a molecule to be aromatic. Okay? The first thing is that the molecule must be cyclic. This is aromatic. It is cyclic. What do I mean by cyclic?
Or the ring.
It's a ring. How do I know whether or not that's a ring or not?
They're all connected.
They're all connected together. But really, if you think about it, if I put my pencil on one carbon, I can go to each and every one of the carbon atoms without having to lift my pencil to get back to the starting point. That's how I know it's a ring. Okay? Now, if I take this molecule and I open it up, is it aromatic now? It cannot be aromatic anymore, even though all I've done is open the ring and added 2 hydrogens. It is no longer aromatic because it doesn't satisfy the first rule. It must be cyclic. So on an exam, if I gave you something like this and it wasn't a cycle, by definition it can't be aromatic. Just cross it out. If I asked you to identify an aromatic compound. Okay?
And aromaticity has nothing to do with odor, just to be clear on that.
That's right. From a chemical point of view, it has nothing to do with odor. I can give you some aromatic molecules that don't really have much of an odor. I can also give you some aromatic molecules that really stink. And some that smell good. But that's not what we're talking about. Okay? So rule number 1, what?
Cyclic.
It must be cyclic. Rule number 2, it must be planar. All of the atoms of the aromatic ring must be in the same plane. How do I know that that's planar?
Put it on the table.
Put it on the table, all 6 atoms fit on the table, right? That is planar. Everything's in the same plane. Okay? If you look at the example here, cyclooctatetraene, it's a cycle. It's got 4 double bonds that are alternating, right? But it's not aromatic. It is not planar. When you build that molecule and you try to hold it down, it will always fold up into a tub. It is actually tub-shaped. Okay? And therefore, it cannot be aromatic.
Can they be not a 6-member group? Like aromatic molecules, can they be like a 3?
They can.
Or 4?
It can.
So it doesn't have to be 6.
Doesn't have to be
It doesn't have
6.
to be 3 alternating bonds.
That's right.
But the bonds still have to be alternating.
They do.
But they don't have to be 3.
They don't have to be. Right? If that molecule was planar, it's still not going to be aromatic. There's another rule, right? And in fact, what you find is that if you take cyclooctatetraene, which you can buy, and you add bromine to it, it reacts just like you would expect. It reacts like double bonds. It's just 4 double bonds in the same molecule, okay? But it's not aromatic because it's not planar. The third rule, the molecule must be completely conjugated. That means we have this double bond, single bond, double bond, single bond, double bond, single bond motif. It's completely conjugated.
So conjugated means alternating bonds.
That means alternating bonds. So double, single, double, that's conjugation. Okay? And so benzene satisfies that, doesn't it? It's conjugated. This one is not. Right? Because it's double, single, single, single. going around the ring, right? Not conjugated. 1,3,5 cyclohepta triene. Double, single, double, single, double, single, single, going around the ring. It's not completely conjugated. Okay? We don't have a complete conjugation there, so it can't be aromatic. It's not aromatic either. Okay? So, Selena, when you said, what if we had two double bonds? That's this exact example. It will react like those are two double bonds. You can add bromine, you can hydrogenate. Everything that we learned about that you can do with a double bond will happen here, but not there. Okay. And then the fourth criterion is Huckel's rule. This is definitely something for you to write down in your notes. Huckel's rule. Okay? Huckel's rule is that the number of pi electrons must be equal to 4n plus 2. 4n plus 2 equals the pi electrons, where n is any integer, including 0. How many pi electrons do we have in benzene?
6.
We have 6. Each double bond is 2 pi electrons. 1, 2, 3, there's 6. So I can do the math. 4n plus 2 equals 6. 4n equal 4. If I do the math, right? Divide by 4, divide by 4, n equals 1. Does that satisfy Huckel's rule?
Yeah.
Absolutely. Okay? Absolutely. You can get into molecules that look like this. This is called naphthalene. This is what's in mothballs. It is an aromatic compound. Okay? It's 2 rings put together, but it is cyclic. I can start at any carbon, and I can go all the way around and get back to my starting position. It is completely conjugated. Double, single, double, single, double, single, double, all the way around. It is planar. If I built a model, I would see that it lies in a plane. And it also satisfies Huckel's rule. How many pi electrons do you see there? 10. So 4n equal 8, n equal 2. That satisfies Huckel's rule. All 4 of these things must be present for a molecule to be aromatic.
So, the way you're working out the equation, is there a value that n cannot be that would tell us it's not aromatic? Or does it just have to be like greater than 0 for that to be?
Okay. So let's do this. We're jumping ahead a little bit, but that's okay. Take that. Let's go through the rules.
Can you explain where you got the 10 first?
Sure.
Really quick?
2, 4, 6, 8, 10. Yep.
So 4 on that one?
Yeah. Well, let's go through all the rules, though, right? Is it cyclic?
Yes.
Is it conjugated?
Yes.
Yep. Single, or excuse me, double, single, right? It's conjugated. You don't really know if it's planar, but I drew it as a plane, so let's say it's planar. Okay? And now the last thing that we have to do is satisfy Huckel's rule, right? So 4n plus 2 equal what? 4. So 4n equal 2. So n equal. Does that satisfy Huckel's rule?
No.
It's not aromatic. This molecule is.
It has to equal the number of,
N has to be a whole number, including 0.
okay, it has to be a whole number.
Yeah, 0, 1, 2, 3, 4, 5. It can't be 1.5. It can't be a half. It can't be 3/4.
But if it equals 4, then it's not aromatic? That what the second,
This one?
now is that what the second rule is saying? compounds that contain 4N pi electrons are especially unstable, considered anti-aromatic.
Yeah, I haven't talked about anti yet. I jumped ahead a little bit, okay? But it's clearly not aromatic, right? Because it doesn't satisfy Huckel's rule. It does satisfy this other rule of 4N equal the number of pi electrons, and that's called anti-aromaticity. So if aromatic is more stable than expected, what would anti-aromatic be?
Less stable than.
Less stable than expected. And in fact, you can't make that. Actually, you can. We have. It lasts for about 50 nanoseconds. But it's so reactive that you can't isolate it. Okay? Because it doesn't satisfy Huckel's rule. Okay? Now, you can have molecules that are just regular molecules. Like that one. Okay? That doesn't satisfy Huckel's rule, or does it? Without doing my reduction of my fractions like I should if I was a good mathematician, and I'm not. Okay? So this doesn't satisfy Huckel's rule. Would it satisfy this other rule?
Can you go over that other rule again? Like, what is this?
4N equal the number of pi electrons? You just no plus 2?
No plus 2.
Yeah. So you might expect, right, that this molecule would be more less stable than you would expect, right? But yet I just gave you an example of where we add bromine across it. And I told you can buy it. So why is it not anti-aromatic? Remember, there are 4 rules. It must be cyclic, must be completely conjugated.
It's not plain.
It's not planar. I told you it was tub-shaped, right? This is why it's tub-shaped. Because if it were planar, it would be so reactive that it couldn't exist. So it folds up into a tub. That's why it folds up into a tub. Yeah.
Can you tell me what it means to be cyclic?
Sure. So cyclic means if I start somewhere, right, I can go around without lifting my pencil and get back to my starting point. That's a cyclic molecule. Okay? So, these are the values that you can have for Huckel's rule. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on and so forth. Okay? And here's some examples of molecules that are called annulines.
Is that not a crown ether?
That's not a crown ether because crown ethers have oxygens. But they kind of look like a crown, don't they? They're just all carbons. These molecules are actually aromatic, and they actually sit in a plane. When they made these and got the crystal structures, all of those atoms were in a plane. This is called 14 annulene because there are 14 carbons, right? So there are 2, 4, 6, 8, 10, 12, 14 pi electrons. Okay, so 4n plus 2 equal 14. You can solve for n. N is 3. It's aromatic. 18 annulene is also aromatic. Okay?
So, you said that Huckel's rule must be satisfied for it to be aromatic. Then you said anti-Huckel's rule?
It was the anti-aromatic rule.
Anti-aromatic
Just 4n equal the number of pi electrons.
Okay, and what does that mean?
It means that if all 4 of those things are satisfied, cyclic, planar, completely conjugated, and 4n, then it's anti-aromatic, and it's more reactive and would not exist for very long.
Okay. So that's what,
Yeah.
So the anti-aromatic formula is 4n equals 2.
No, 4n equals the number of pi electrons. There is no plus 2.
Okay.
Yeah.
and when will we use
Well, for example, if I gave you a problem where I told you that a molecule was cyclic, planar, and completely conjugated, and I asked you, is it aromatic or anti-aromatic or non-aromatic, you'd have to do the calculations.
So you could do like both.
Yeah. If a molecule doesn't satisfy either one of Huckel's rule, it must just be a non-aromatic molecule. Okay, it's just a molecule. Okay, but if you have satisfying Huckel's rule, then it's an aromatic compound. If it satisfies the other rule, then it would be an anti-aromatic compound. So here's that example again, right? And both of these molecules would be cyclic, planar, and completely conjugated if you built the models for them. One would be perfectly stable and last for hundreds of years. One would be anti-aromatic, very reactive, and gone in a fleeting moment. Okay? And again, you can figure all that out doing the calculations. But all of these calculations really come down to doing orbitals. Okay, we've learned a little bit about orbitals. I just want to explain this to you really quickly. I don't really want you to memorize too much of this, okay? Just want you to be familiar with it. It turns out that the molecular orbitals of benzene are why it is so stable. All of these other things were observations, but it really comes down to the orbitals. And what we found is that if you look at the energy of the orbitals, which you can get from this so-called Frost circle diagram, you can see that the three orbitals that contain the pi electrons are lower in energy than you would expect. And that's why you get the stability out of it, okay? All this other stuff just helps us explain it, okay? Helps us understand it. But it really is all about the orbitals. So if you take a higher level chemistry class, they're going to talk to you in terms of orbitals. And so it's kind of important to think about that. So there's molecular orbitals. But I am not going to examine you on the exam in terms of molecular orbitals. We're just going to focus on the 4 rules, right? What were the 4 rules again? Rule number 1?
Cyclic.
Rule number 2?
Planar.
Rule number 3?
Completely conjugated.
Rule number 4? Huckel's rule, 4n plus 2. That is right. We will have a quiz over chapter 8 on Wednesday. So be prepared to have everything ready for that. I will send out some emails about the workshop. You all will be getting your exams back in lab, and I will see you all later.
Well, we won't have that Thursday. I don't have it.
Oh, that's right. Oh, I don't know who's in. If you're in Thursday night's lab, email me and I will send you your.
What about that afternoon?
What about that afternoon?
Well, mine's at 1 to 3.
Thursday? There's nothing Thursday.
So that's my last.
Everything's canceled Thursday is what I'm saying.
Okay. Sorry.